let's continue. And here, let me just dwell on the concept of randomization a little bit more, because later on, I'm going to make kind of analogs of techniques, analogs in the randomized experiment to the techniques used in causal inference. So what is randomization? Randomization is not haphazard or casual choosing or selection. Let's say I grab a paper, then I can just kind of casually write down some name and assign some people at my will to a certain group, then look at the mean outcome, then compare. No, it is to systematically rule out kind of patterned attributes. So why randomization? Well, ideally, different treatments are experimented on the same subjects and then compare. But why people don't do that is because there are a lot of problems related to confining issues, contamination. So for example, I do one experiment on this individual A, and after a while, if I switch to another treatment, obviously there could be undoubtedly there could be some residual effect from the first treatment, right? Kind of permeated into the second treatment. You never know. You don't know when is the real break occurs. Let's say wash out all the residual effect of the inference of the first treatment. And there are also issues about infeasibility, like COVID-19 in this case, right? I mean, it's just impossible, infeasible to apply two vaccines, on the same individual, right? It's time-wise, cost-wise, etc. So care is taken to ensure that no pattern exists between the assignment of subjects into groups and any characteristics of those subjects. So randomization, as Fisher and his colleagues, as well as a couple of precursors, prove that randomization can eliminate the biases that are described there and help us arrive at reliable conclusions. Here I'm talking about the difference in the average outcome of different treatments. Okay, and there are a couple randomization categories. First is called completely randomized design. If experimenters use this design, then objects or subjects are assigned to groups completely at random. How to do that? Well, there are a couple of things we could do. We could use some physical devices, like we could toss a die, a fair die, flip a coin, or we can shuffle cards as described in the book by R.A. Fisher, right? A deck of cards. Then he says, well, we can use the remainder, division of 5, then assign 1 to 5 varieties of the farm crop to 1 to 5 plots. Or we can use a table. Back then, there was not a computer available. Today, we can use some random number generator or a random number table.
Sir?
Or computer. Yes. Anyone?
Never mind.
Okay. And the second is randomized block design. And well, under this design, experimenters group people into homogeneous blocks with regard to key factors, for example, age, sex, education. Okay, so after people are grouped into these homogeneous, what's called blocks, then we randomize, assign subjects in these blocks into different treatment groups. Okay. It is used when experimenters know the factors that would confound the results or outcomes. Here I only describe two just to begin with, to give especially those who don't have any ideas about randomized experiments. But there are a myriad of kinds in practice. You know, as I checked this morning, there are probably 20, 30 kind of subcategories about how to conduct randomized experiments. To summarize, fully blocked design here, block design or fully blocked design in general dominates complete randomization. That is the first randomization category that I was just describing, according to Gary King. In terms of imbalance, model dependence, efficiency, power, bias, and research cost. So in general, the second big category, randomized block design, that is, we first group people into homogeneous blocks, then randomize, is much better than the first one.